Hello, welcome to Atomic Physics, the 7th video, in which we're going to look at what's called the mass defect, atomic mass units and binding energy. So we're going to cover a few things in this, but it is fairly logical, hopefully. So this is all about nuclear energy and where that energy comes from, be it the sun or in a nuclear reactor, or just looking at an individual reaction and what happens in terms of energy. So where does it come from? Okay, first thing we need to learn about is the mass defect. Now, the mass of a nucleus is always less than the combined individual mass of its constituent nucleons. Okay, now in this case we're talking about the nucleus, so we're ignoring electrons, because electrons don't have anything to do with what's happening in the nucleus. Before, and in some cases, we consider electrons for one reason or another, but if we're actually looking at the energy that's coming out of a nucleus, we can pretty much ignore the electrons. So this is where it is. If you weigh all the things that make up a nucleus, it weighs less than the nucleus. So it's a bit of it's basically the missing mass is in the form of energy released when the nucleus is formed. So an example is deuterium. Its nucleus has a mass of 3.34364 times by 10 to the minus 7 kilograms. Notice all the decimal places. We're getting to be very accurate now, because there is a high degree of accuracy in all these numbers, and we're talking about lots of decimal places usually. However, when we look at the sum, because deuterium is, if we remember, an isotope of hydrogen, and it contains a proton and a neutron in the nucleus. It's the heavier of the hydrogens. And so if we add up the mass of a proton and the mass of a neutron, we get 3.34, that's the same, but then it goes 7.6 times by 10 to the minus 27 kilograms. So the two masses are not the same. And this is actually always going to be less than this, than the constituents. And so 0.004 times by 10 to the minus 27 kilograms is missing. Now that doesn't sound like much, but and this missing mass is referred to as the mass defect. And before we go any further, we just need to make sure we know what atomic mass units are, because from now on we're going to interchange using kilograms and atomic mass units, and previously we were just talking in kilograms, but it's actually sometimes more convenient to use what are called atomic mass units, and it's most commonly used with atomic equations, and you may have been using it in physical science or chemistry, so you may be familiar with it. Basically, it's saying that one atomic mass unit is equal to 1.6606 times 10 to the minus 27 kilograms. Okay? And that comes from a 16th, is it, or a 12th of carbon? I think it's a 12th of carbon, 12 atom. And if we were to look at it, like previously we've said that proton and neutron weighs the same. But when we're dealing with atomic physics, they don't weigh the same, because we're looking at all those extra decimal places. Previously we've just been rounding them up and rounding them down. And so if we convert the masses of a proton, neutron and electron into atomic mass units, we get these values here. And you can see that the proton and neutron are not the same at the third decimal place. And these are the values we need to use. So the mass defect is actually the mass that's been converted into what's called the binding energy, and sometimes people might refer to it as the unbinding energy. And what we mean by the binding energy is that's the energy that holds the nuclear particles together. It basically overcomes the huge electrostatic forces of repulsion between all the protons. And basically it is what we would refer to as the strong nuclear force, one of the strongest forces out there. Only acts over a very short distance within nucleus, but it's a very strong force and a fundamental force. And so this binding energy relates to overcoming this electrostatic repulsion. So it must be very strong. And we can use E equals mc squared to calculate this binding energy from the mass defect. So if we can work out the mass defect, we can work out the binding energy, and we can then work out the energy. We can also express the binding energy in units which are referred to as MeVs, or mega electron volts. So we've been introduced to electron volts before. It's a convenient unit to use in atomic physics, and we need to recognize that one atomic mass unit is equal to 931 mega electron volts. So and that's on our information sheet. So we might be doing these questions, and we might be working in atomic mass units, and then we might be asked to give an answer in electron volts or mega electron volts, and we might also be working in kilograms, and we might also be working in joules. So these sort of questions can get really test your understanding of units, but you just have to be a bit careful with them. Okay, and this is where our conversion, which is on our formula sheet again, is, and we've used this before, 1 electron volt equals this amount of joules. Now 1 mega electron volt, obviously you just need to move this, change the power that you're raising it to, and that shouldn't be a problem. So let's do a couple of examples just to clear the fog from our eyes. Now we have the nuclei helium-4, calculate the mass defect, and then the binding energy in mega electron volts per nucleon. So the nucleons are the number of particles in the nucleus, and so we need to work the mass defect out first before we can work out the binding energy per nucleon. Now we can just look up the mass of helium-4, and we're given this value here. We then need to make up the components. Now this is using our textbook, and they've thrown in the electrons, which most of the time we don't worry about because it's just a small amount, and it all depends on whether or not this mass contains the nucleus and electrons, in which case we include the electrons. If this mass is just the nucleus, we don't include the electrons. So that gets a bit confusing because there's no consistency in books, between books and between things, so you just have to keep an eye out, and if you're getting a mistake, a small mistake, it may be due to the electron factor. But in this case our textbook includes the electrons, and so we add them all up, times them by 2 protons, 2 neutrons, 2 electrons, and we get the mass there. And so if we subtract this mass, which is the components, from the actual mass, we get the mass defect. And because 1 unit of mass is equal to 931 mega electron volts, we can we times the mass defect by our conversion of atomic mass units to MeVs, and we get our answer as 28.28 mega electron volts. And that's our answer for the mass defect. And if we just divided this number by 4, we would get 7.07 mega electron volts per nucleon. Now the binding energy per nucleon is a measure of how stable the nucleus is, and the larger the binding energy per nucleon, the more stable it is. And if we look on our graph, this is the binding energy per nucleon, and this is the atomic mass number. We may have seen this diagram before, and these are the elements in the periodic table going from here round here to the heavier elements over here. And we can see there's a peak, and there's a region of very stable nuclei around the iron 26, and that's where through processes occurring in the universe, most atoms want to eventually end up. And if we had enough time and not enough things were destroying and breaking things up, if we just had time, all the atoms would eventually end up here. But because our universe is relatively young, in the scheme of things perhaps, we've still got all these elements, lighter elements, and all these heavier elements. Now these lighter elements undergo fusion to become more stable, and these heavier ones undergo fission to become more stable. And that's what they're striving to do. So where does nuclear energy come from? That's the question that we originally asked at the beginning. Okay, if a nuclear reaction releases energy, and not all do, but most do, it will come from some mass that has been lost during the reaction. This is the mass difference in the reaction. Now, this is important. Do not confuse this with the mass defect. Remember, the mass defect is the energy holding the nucleus together. It's not the energy that's released in a nuclear reaction. Okay, the mass defect is the binding energy. What we're talking about is the mass difference in the reaction. And the mass difference is the mass of the products minus the mass of the reactants. And the energy released is this mass difference using E equals mc squared. So we get to use a famous equation where the mass is the mass difference from the reaction. So we just make sure we don't confuse that. Let's do an example. So if 1 gram of substance is converted completely to energy, how much energy is produced? That says. So we go E equals mc squared, 1 times by 10 to the minus 3, because we use kilograms, speed of light squared, 9 times by 10 to the 13 joules, which is a lot of energy. Let's have a look at an example. For the following uranium-235 fission reaction, calculate the energy released per fission, so that's per reaction, and per kilogram of uranium-235 reacted. So here we have uranium-235. It's being bombarded with a fast-moving neutron. We're producing strontium and xenon, and also 3 neutrons are given off. So this is a typical reaction that might occur in a nuclear reactor or in an atomic bomb. And so what we need to do is first of all work out the mass of this side and compare it to the mass of this side, and we'll get the difference being released as energy. So the mass of the reactants, we just look up in the table. We've got 1 uranium-235, 1 neutron, and we've got a total. Mass of the products is strontium 94, xenon 139, 3 neutrons, so we're going to multiply that by 3, and we get a total. Then we subtract the 2, recognizing that it's just an absolute, so it doesn't matter which order you subtract, and we get this as the mass defect, which is really not what we should call it. We should call it the mass difference, even though they call it the mass defect. And knowing the conversion of 1 atomic mass unit is equal to this in kilograms, if we times this by that conversion factor here, we get the mass difference. Okay, let's just make sure is my pen going to work? Come on, old girl. Or old laptop. Doesn't want to work. Thinking about it. Anyway. No. Oh, now it's making little swirly sounds. It's going to crash, probably. Here we go. What the hell are you doing? I'll keep talking over the top of my laptop. No. And so we times our mass difference. Let's cross that out. Hello? No, it just doesn't want to work. And we use E equals mc squared, and that will be the energy that's being released in this reaction. Now let's see if we can move. It just doesn't want to do anything now. Ah, we've got our pen. That took forever. And let's cross that out. Let's cross that out. And alright. Difference. Crikey. This laptop, sometimes it just has a bad day. So that's the mass difference. Alright. Wonder how long it will take me to get the mouse back. If in doubt, ooh, I think I have something. So we need, oh god, we need to remove all that writing. That was hardly worth it, was it? Okay, come on, old girl. So, next part was the energy per kilogram. So they've done a little bit of tricky stuff here. What they did is the mass of one uranium-235 atom, and because uranium-235, it weighs 235 atomic mass units. Okay, so we then use the conversion of atomic mass units to kilograms, and we get the mass of one atom. And then to find the energy released in 1 kilogram, we divide 1 kilogram by the mass of one atom, and we multiply it by the energy that is being released by one reaction. So we multiply it by how many reactions would it be occurring in 1 kilogram, and we get the total amount of energy, which is massive. Again, hope that makes sense, even with my little pointer issues. So you should now be able to do some chapter questions in 27, and there's a whole lot of set 16 questions that will put this into good practice. And in the next video we're going to look at detecting nuclear radiation. See you.